So, beginning with a logistic equation, y prime equals ky times L minus y. Assuming y of 0 equals y naught, we obtain this form, which can be put into a form that tells us that for small t, y is approximately equal to y naught e to the k lt. That's provided that t is small and y naught is much less than L. Now, here's a sketch where y naught is maybe 1/10 as great as L. That might be small enough. It's at least small enough to exhibit the overall behavior of this function, so that what's going to happen is when y naught is small, this is very close to y naught e to the k lt, which is an exponential function with growth rate k. So we start out close to exponential function with growth rate, I said k, it would actually be kl. And then as t gets larger, we're going to approach our limiting population L, so that this exponential gets modified, eventually slowing its growth and eventually approaching L as a limit. We can do the calculus of this function. We can find the inflection point. We can find where the function is concave up, where it's concave down, using techniques of first semester calculus. And that's, those derivatives are a little bit messy, but they're manageable. So this is the picture we end up with, assuming that y is much less than L. Now, what if y is greater than L? So what if y is greater than L? Remember, we had a solution. This solution depended on two conditions. One was that y of 0 equals y naught, and also y was less than L. And the reason this was important, you recall, had to do with the absolute value in our solution. Now, if y is greater than L, that's going to change the nature of our solution slightly. And we'll see that very shortly.